Hello everybody, welcome to our third session. Last time we introduced basic mathematical concepts, especially relations. Today I want to talk about a special type of relation that's called an ordering. You have seen orderings before. For example, on the natural numbers, you've seen the ordering less or equal. Or on the integers, you have seen the ordering of divisibility. So these are orderings, and they play an important role in discrete mathematics, but they don't only exist in natural numbers and integers. Let me actually give you a completely arbitrary example of an ordering. We want to compare apples and oranges, although people tell us that you cannot do this. So these two fruits, there are actually, a lot of things we could compare. We could compare the taste, the price, the vitamin A content, vitamin B content, vitamin C content, and so on. So there are lots of parameters we could compare. For today, let's actually focus on two parameters. The first is the vitamin C content. The other is the iron content. So here we see this is the vitamin C and the iron content of apples and oranges, and to spice things up, let's add some other food items. So how can we represent this data nicely? Well, let's make a two-dimensional chart and let's put our food items into this chart. So now I want to define an ordering. I want to say A is less or equal than B if it contains at most as much vitamin C as B does, and at most as much iron as B does. Okay, so that's my ordering. Let's see how it looks like here. So for example, clearly the apple is smaller than the broccoli, it's smaller than the kiwi. The orange is also smaller than the broccoli, and both are smaller than the chili. The apple is also smaller than the spinach. But apples and oranges are incomparable because the orange is richer in vitamin C, but the apple is a little bit richer in iron. So they are actually incomparable in this ordering. And to make it complete, we would also have to insert an arc from the apple to the chili and from the orange to the chili, because also the orange is smaller than the chili in this ordering. Okay, this is an example of an ordering. Now it deserves a formal mathematical definition. Okay, are you ready for it? Let's go. So you have a set, you have a relation on it. So for example, we could depict the relation by these little arrows. Let's say this just means A, B is in the relation and so on. And the relation can have certain properties. So for example, we say R is reflexive if x is in the relation for all x. So here it basically means we have these little self-loops around each vertex. Second, we say R is transitive if, let's say you have x, y, and y, z appears in your relation, then you always have x, z in the relation. So let's draw a picture. If you have x arrow y and y arrow z, then this implies x arrow z. This is transitive. And R is antisymmetric if, well, this is a little bit counterintuitive, if x cannot be smaller than y and simultaneously y smaller than x unless they are the same. So basically it means you don't have such a thing. Okay, so now it works. Okay, great. So something like this doesn't happen. This means antisymmetric. So let's quickly summarize it. A relation that is reflexive, transitive, and antisymmetric, that's called an ordering. So now you can go back and check that these three properties actually hold for the less or equal relation on natural numbers, for the divisibility ordering on integers, and for our vitamin C and iron ordering on fruits. Some relations have the following bonus property. So for example, consider the natural numbers together with a less or equal. You always have a less or equal b or b less or equal a. Consider the divisibility. Well, divisibility we should actually write integers, not natural numbers. It could be that a does not divide b and b does not divide a. So this is possible. So it seems here that the less or equal relation has a bonus property. It means if you have two elements, you can always compare them. But the divisibility ordering doesn't have this. For example, 3 doesn't divide 7 and 7 doesn't divide 3. So this bonus property is called linear. It's called a linear ordering, sometimes also a total ordering. Just keep in mind, some orderings have this property, some don't. Okay? If it doesn't, then we call it a partial ordering. All right, so here is a summary. Reflexive, transitive, antisymmetric, that's an ordering. If in addition it's linear, it's a linear ordering. Cool. So let's look again at our ordering on food items. Let's look at this arc from the apple to the chili. It's actually redundant because even without the arc, we would know that the chili is larger than the apple by transitivity, right? We can just go from the apple to the broccoli and then up. So this arc is actually redundant. We can remove it, and the same with this arc. And now we are left with the non-redundant arcs. And this has a name. This is called the Hasse diagram of an ordering. Again, this deserves a formal definition. We call x an immediate predecessor of y if x is smaller than y and there is nothing in between. So you cannot find anything that is strictly between x and y. So for example, the kiwi and the chili are immediate predecessors, but the apple is not an immediate predecessor of the chili because the kiwi is in between. The broccoli is in between too. Okay, so now if for every immediate predecessor you include an arrow xy, then what you get is the Hasse diagram. And there is actually a cute lemma. If you have an ordering and S is a finite set, then the Hasse diagram uniquely defines your ordering. So if I show you the Hasse diagram, you can reconstruct the ordering. Now this condition, S to be finite, is actually crucial. For infinite sets, this lemma might be false. For example, consider the set 0, 1, the real interval, together with a smaller equal relation. So what is the Hasse diagram of this ordering? Think about it. Okay, we need some further important definitions concerning orderings. So first of all, if x is less or equal than y, or vice versa, then they are comparable. Otherwise, they're incomparable. And if you have an ordered set, and you have a subset, and everything in C is mutually comparable, like A and B are comparable for all A, B in C, then we call C a chain. Like it's a subset that is linearly ordered. And if you have the opposite, if any elements, all elements are pairwise incomparable, then A is called an anti-chain. So it's a subset where nothing is comparable. All right. This is chains and anti-chains. Now, an element is maximal if nothing is larger. If there exists no y in S that is larger. And it's called minimal if there exists nothing that is smaller. In general, this is different from the following definition. X is a maximum. It's a maximum if it is bigger than everything else. And it's called a minimum. It's called minimum if X is smaller than everything else. So just be aware that these two definitions are not the same in general. If your order is not linear, these might not be the same. Here is a summary where everything is nicely written. And here is an exercise for you. You should find the largest chain, largest anti-chain, maximum, minimum elements, and minimal and maximal elements in our food item ordering. One last thing, then we are done for today. Here we have an ordering S in this. And now suppose I'm only interested in this subset, X. Then my ordering induces a suborder, right? I just take the ordering, I restrict it to X, and I get a new ordered set. So every subset of S also inherits the ordering. This is called the induced suborder. All right, that's it for today. Here are some nice exercises. Those without star are quite simple. You should be able to solve them if you have understood the material of today. Those with 2 stars actually requires some non-trivial proof. So here is the first set, and here are some more exercises. All right, thank you for today. See you next time.